All right. So more responses and stuff I get from you, the quicker we get out of here today. Might get out of here a little bit early if we kind of keep it moving. Couple of things I want to mention before we get started. So you'll see after class pop up the next final module reading, module 13, right? You'll also have the quiz from this week, module 12. And I'm also going to change the due date. I mentioned this on Tuesday, but I'm changing the due date of this pack back assignment to be the end of the day Monday as well. So you'll see all of that get popped up there after class between 11 and 12. So everything will be due at the end of the day on Monday. Now that's the last module reading. So if you look at the syllabus, I forget to mention this sometimes. I always mention the quizzes, but I actually only take your best 10 module readings as well. So early next week, after that due date is passed, I'll get updated on Canvas what your final module reading score will be. Right? I'll drop your lowest and then kind of put up what your score is. Right. So right now, it's kind of like worst case scenario. If you just don't do the final one, your grade would be whatever it is. Right. If you do the last one, I'll drop your lowest and kind of get those scores updated. Should be probably not before class Tuesday, since the due date is the end of the day Monday, but Tuesday after class, I'll kind of get Canvas updated to reflect that. Okay. Now we still have one more quiz, which would be the module 13 quiz, and then 2 more in-class quizzes next week. So we're getting close to the end here. Things will kind of start changing a little bit on Canvas so I can give you a more accurate idea of exactly where your grade's at. I'll mention all these things in class as I do them as well. Okay. Also, I'm triple checking with my CL leaders. I've gotten a lot of questions from you guys. I'm not aware. I've talked with both of them. None of them let me know. CL sessions, I know it's Easter weekend or whatever, should be the same. No one's told me they're canceling theirs. And so tonight's sessions and Sunday sessions should be taking place kind of as scheduled. Okay. If for some reason, like I said, I'm going to triple check, send an email after class. If something changes, I'll put an announcement up on Canvas. But as far as I know, everything is good to go. Okay. Other than that, I think that should take care of all the housekeeping stuff. Any questions for me before we just jump into material here today? Okay. So we left off last class talking about the prisoner's dilemma, identifying from a normal form matrix, Nash equilibrium. We'll start out with an example that is a little bit different, but it puts in a context where you can see this game theory stuff is not just used in markets and kind of traditional economics, but decision-making, and we can even see it often used in political science. Okay. So here I've got this example where I kind of laid it out, thinking about you've got 2 candidates, Republican, Democrat, RD here, and they can run negative attack ads or not. All right. So if I run negative ads and my opponent doesn't, they're going to lose a lot of votes. I'm going to gain some, but some people will just decide, hell, I don't want to vote for anybody. Right. If we both don't run attack ads, well, nothing changes. And if we both run attack ads, we might draw some votes from the other person, but we're also going to convince a lot of people that there's now no one I want to vote for. So here I've kind of got it written out, just kind of thinking about the incentives that would exist. We'll talk through it. Once again, we did a lot of prisoner's dilemma stuff last class, so I'm not going to rehash it a lot. But I want to start out with it to kind of just think about these normal form games. So let's say, how would I solve this? I've got 2 individuals, the Democratic candidate, the person on the left. We said their payoffs will be on that lower left-hand side. Person 2 is the Republican candidate. They're going to be the person on top. Their payoffs are going to be on the upper right side. Okay. Now, I color-coded them here to make it a little bit easier as well. All right. So what we're going to do with these normal form games is we're identifying what each person's best response is to all the other possible choices of the other person. Now here we're keeping it easy where each person only has 2 choices. So when I was drawing these out, and I'll be pointing these for you here today, I was usually like putting my hand or putting the markers over. We're really just singling out one decision at a time. So let's think about if this Democratic candidate decides not to run attack ads, what should the Republican candidate do? Well, if they don't run attack ads, they don't lose or gain any votes. So 0 is kind of the payoff. If they run attack ads, they're going to gain 1,000 votes. So if they're acting out of self-interest, what's better? Having the same number of votes or gaining 1,000? Gaining 1,000, all right? Now, so I circle that. Now, what if the Democratic candidate makes the other decision to run attack ads? Well, there, what should the Republican candidate do? If they don't run ads, they lose 3,000 votes. If they do, they only lose 2,000. What's better? Losing 2,000 votes as opposed to 3,000. So we would say the Republican candidate has a what? Starts with a D. Dominant strategy. They're always choosing to run these negative ads, regardless of the choice of the other candidate. Now, these are symmetric payoffs, so it's going to be very similar, but we would do the same thing now. Let's assume the Republican candidate doesn't run attack ads. What does the Democratic candidate do? Well, if they don't run ads, they don't lose or gain any votes. If they run them, they gain 1,000. So that's better for them. What about if the Republican candidate doesn't run ads? Well, there, if the Democratic candidate doesn't run ads, they lose 3,000. If they do run negative ads, they only lose 2. What's better? Only losing 2,000. So we said once we've identified these best responses, the non-technical way of identifying our equilibrium is any box, we have 2 circles in it. Well, what is that really saying? It's a combination of strategy choices where we're both best responding to what the other person is doing. Okay? So we're both best responding to what the other person is doing. Now, in this case, if I'm just worried about losing votes, what would this Nash equilibrium also represent? So I set this up. I said we did a lot of these examples last class. This is another example of a prisoner's dilemma. Why? The definition of a prisoner's dilemma is a Nash equilibrium where if we could go to a different combination of strategy choices, both people could be better off. So here, if I were to go over here, are both people better off? No, only the Democratic candidate, right? They're only going to lose, or they're gaining votes instead of losing, but the Republican candidate would actually lose more votes. However, if we could somehow get to this point where they both don't run negative ads, are both of the candidates better off? Well, neither of them are losing votes. Everything's staying the same, so that would technically be better off there. So this would be an example of a prisoner's dilemma. Okay, so we end up with this equilibrium where both people are worse off than if we had a different combination of strategy choices. Okay, so there, what do we actually have? Right, so if I look at this Nash equilibrium, both candidates are going to lose votes. I guess technically, do the candidates really care a whole lot about this? If we're both losing the same number of votes, what's happened to my chance of winning? Hasn't changed. So if instead I had the, here I was saying that the candidates just cared about people voting. If they just cared about winning, they're actually no better off if they both run attack ads or if they both don't. But who's going to lose out a lot? Society, right? If we think about society's payoff, society doesn't really care. I shouldn't say they don't really care. Ultimately, their incentives aren't about who wins or loses. One thing that society might care about is just having a voting public, like people actually vote. So here, how many people are no longer voting? 4,000. Up there, no change. So for society, we would like more people to vote. We would actually like to be up there where nobody runs these negative attack ads. So this Nash equilibrium would cause something we talked about in other modules for society, which would be a what? Negative externality, right? So we can identify some of these Nash equilibrium, and we're trying to connect the dots between all these things we're talking about. This would also kind of let us know, oh yeah, if we cared about society's payoffs here, society is going to be worse off in this Nash equilibrium, right? Maybe even I built this out to where the payoffs were just like the chances of winning. Maybe the candidates aren't any worse off, but society would be, right? We're just having people abstaining from voting, okay? So this was kind of where we left off thinking about this prisoner's dilemma, kind of mentioned connecting it with like negative externalities here. We also started thinking about, in the context of markets, what this prisoner's dilemma looks like, okay? So I've got, we talked a little bit last class that if I've got 2 firms, even if they try to agree to act like a monopolist, we said that the prisoner's dilemma is there's incentives for both of them to like undercut each other's price. So I'll work through a model kind of like that, and we'll think through, we did this last class, why maybe they'll cooperate, okay? So let's start out. And I'll just think about, well, let's do the monopoly price and a perfectly competitive price, right? Now, obviously in practice, these firms could make like any choice in between those two. But we said like the same sort of intuition would like continue to push them to continue to always be the one that undercuts the price of the other firm a little bit more. So if it's easier to think about, maybe this is a price of 50, this is a price of 25. If we both set a high price, maybe we're splitting monopoly profits, okay? If we both set the perfectly competitive price, what would profits be? 0. If I'm the one that undercuts the other person's price, what's going to happen? Everybody's going to want to buy from me, but I'm charging a lower price. So maybe I increase my profits, but not, I don't double them or anything like that. Now, if I'm the one who's charging a high price, nobody buys from me. I don't sell anything, but maybe I still have some costs, right? I have my fixed costs or whatever it is. Okay. And then same kind of idea here. If firm 2 undercuts the price, they're going to benefit, increase their profits. Firm that continues to set a high price, they're not going to sell anything, but they have their costs. Okay. This is kind of a little toy example setting us up. We'll kind of think how we would solve this. And then what happens if this was a repeated game? So I won't push you guys quite as far as like actual repeated game models, but I'm going to show you a way we can think about when things are repeated, how you could look at it in these normal form game matrices, and that I could expect you to know how to solve. Okay. So I was using these markers last class to kind of rule out, right, to make it, I think, a little bit easier to say, what are the 2 decisions that firm 1 has? They can set a high monopoly price or a lower, closer to the perfectly competitive price. For firm 2, what is their best response to that? If they set a high price, they get 100. They set a low price, they get 150. So that's better, right? 150 is better than 100. So we'll identify their best response. Now, if firm 1 makes the other choice, where they set a low price, what should firm 2 do? Well, if they set a low price as well, they get 0. If they try to charge a high price, they get negative profits. That's not, 0 is better than a lot. Someone had said, well, why is it better than negative? Negative is losses. I'd rather have nothing than lose something, right? So here we've got firm 2 has a what? They're always setting a low price regardless of what firm 1 does. So they have a dominant strategy. We would do the same thing now. If firm 2 chooses to set this high price, what should firm 1 do? 150 is greater than 100. If firm 2 sets a low price, what should firm 1 do? Okay. So we have a Nash equilibrium where they're both going to set this perfectly competitive price. Okay. So what would this also represent? It's a Nash equilibrium, but it's also a prisoner's dilemma. Because if we could somehow agree, we could both be better off. Okay. Now, I don't think I quite got here last class, but let's think about, why do we stop at that perfectly competitive price? So let's say, I don't know, PC, sorry. Let's say I go even lower, right? You go to a price of 20, right? So we said here, just kind of representing this, just to kind of give you a flavor of both. Instead of writing this like person 1's payoff persons 2, we can also use this like diagonal system. Now it still follows the same sort of protocol. The person 1's payoffs are on the left, person 2's are on the right. So here, perfectly competitive price, that's kind of where we're starting out here. Both have profits of 0. Now, if I kind of undercut that price a little bit more, here we get kind of a weird one where if this is the perfectly competitive price, if I lower the price even more, what's going to happen? Well, profits are 0 when we're at a price that's the lowest possible value of my average total cost curve. So if I lower the price even more, what's going to happen? My profits will become, so maybe this is like negative 10, but my price is lower, so everybody's buying from me. I'm still going to have losses, but now maybe I've caused the other firm to have even larger losses, right? They can't sell anything and they have their costs. Same kind of idea over here. If I charge the lower price, I'm still going to decrease my profits. Now I'm below that minimum point of the average total cost, but maybe the other person's hurt even more. If we both lower, we're splitting demand again, but price is below average total. Maybe we've got these values. Okay? So if we kind of go through and solve this, well, actually, let me keep it the same as color is the same as up here, right? So if firm one chooses that perfectly competitive price, what should firm two do? Set the perfectly competitive price. If firm one sets a lower price, what should firm two do? Actually, here it's kind of weird. We end up with they should set the lower price as well, net smaller negative value. And then we can kind of go through this. For firm one, if firm two chooses that perfectly competitive price, they choose the lower price. Well, here we would actually end up with a game, and this can happen. I think I might have shown you one example last class, and we'll look at a couple more today. You don't always have one equilibrium. You can have multiple equilibrium. Okay? Now, in this scenario, the way that I constructed these payoffs, we end up with either the perfectly competitive point will be our equilibrium, or we're going to end up with an equilibrium where both firms have negative profits, right? Now, in practice, if we have negative profits, what's going to happen? In the long run, one firm is going to exit, right? So you could actually think about in the long run, I'm not going to have my fixed costs. I'm just going to exit the market, and all these payoffs would be zero. So in practice, we see like this is the equilibrium that the firms stop at, right? Because there's no incentive to try to keep undercutting the other person's price, because if I do, I'm just ending up with larger negative values, right? And if we both undercut each other, we continue to lower that price, we're actually not going to have negative profits here. Technically, one of us is, we're going to like leave the market. We'd be back at zero. Now we go back to a monopoly. The other firm enters. We kind of see that profit push back down to zero as well. So we never see kind of firms go below or like undercut each other's price anywhere below profits being equal to zero, because there I have negative profits. Why would I do that? Right? I'd be better off just having zero. So this was kind of a weird scenario where like our equilibrium, kind of this Nash equilibrium, was actually good for society. Because what did it do to the price? It lowers it from that monopoly price down to the perfectly competitive price. Any questions on that before? This is more for me. I can show you that there are games where you have multiple equilibrium. Now, in practice, so if we use this model, this is like we're thinking about they're making decisions in one time period. Well, what actually happens? We set prices today, tomorrow, the next day. Even if we do this yearly, I set them this year, next year. So you can actually think about how could I take these values and think about this in more of a repeated game kind of context. Okay. So let's think about the same sort of idea where I can set perfectly competitive or the monopoly price. But now I think about, let's say these firms want to work together. Okay. Well, if we both set the perfectly competitive price for the next 100 years, what are our profits going to be? Every year they would be zero. So nothing really changes there. But if I will work with the other firm as long as they never break the agreement, as soon as they break the agreement, I stop working with them. So let's say we agree to work like a monopolist, and we both set a high price. If I continue to do that, what would my payoffs actually be? Well, it would be 100 for the next 100 years. So I'd be at what? My commas get kind of weird. 10,000, right? So I'm thinking about not just the payoffs of one time period, but if I continue to kind of work with the other firm, I don't just get 100 today. I get 100 today, next year, the next year, the next year, for the next 100 years. So my actual payoffs are going to be much higher. Now, let's say I break the agreement today, right? So let's say we're in year one. We're going to keep playing this game for the next 100 years. I mean, we assume that we're going to be in this industry for a long time. If I break the agreement today, how much do I make? 150, right? What would the other firm lose today? Well, -10. But as soon as we break the agreement, for every other time period, we no longer trust each other. So what are we both going to do? Set the perfectly competitive price. Profits would go to zero. Same kind of idea here. If firm two breaks the agreement in that first year, I'm never going to work with them again. They'll gain $150 that first year, but from every year on out, zero profits. So if we repeat this game, these payoffs look exactly the same, except for what? If I hold true to the agreement, what value is going to go up? the strategy choice of holding true to the agreement. Because if I hold true to the agreement, I'm now not going to just make money today. I'm going to make money today and tomorrow and the next year and the next year. So if we had payoffs that look like this, and then we go through and try to solve this game, if firm 1 is setting the high price, firm 2 is going to hold true to the agreement as well. If firm 1 breaks the agreement, what is firm 2 going to do? They're going to break the agreement. Well, what if firm 2 holds true to the agreement? Firm 1 is going to also hold true. What if they break the agreement? 0 is better than -10. We now end up with this kind of multiple equilibrium, which is, look, if the other person, right, we either both continue to hold true to this agreement and we enjoy really large profits, or if the other person breaks the agreement, the optimal choice for me is to also break the agreement for every other time period from here on out. So we've got multiple equilibrium. Which one are we going to end up in? Can't really say, right? We know we'll end up in one of these scenarios, but it's hard to say which one. Now, if we looked at more complicated repeated games, what's actually going to play out in practice is there's huge incentives that exist here that we're not going to end up at this point, right? We know that, we can come up with some type of like trust model where we see that firms work with each other like a cartel, like OPEC or these different companies that have behind the doors agreements to like restrict quantity or increase prices. The only problem is if we think that we're getting closer to the last period, if we're only going to play this game for one more year, this isn't the game we're playing. We're back down to playing this game. So in the last year, what is my Nash equilibrium going to go back to? Breaking the agreement, because now there's no incentive. We're not going to work with each other from here on out. So if I know that that exists for the other person, what might I want to try to do? Maybe I don't want to hold true to the agreement in the last year because I know I'm going to get screwed. So what might I try to do? Break the agreement 2 years before we're done playing this game? Well, if I know the other person is going to try to do that, I'm going to try to break it 3 years. So there's this kind of like incentive that, yes, initially we're both going to probably agree, hold true to this agreement, set these higher prices, earn higher profits, but there's always going to be the incentive to be the firm that breaks that agreement first, right? Because when I break that agreement first, I'll get a short-term gain, and then we'll kind of zero from there on out. If the other firm breaks it first, I lose some money, and then it's zero on out. So what's better? To be the firm that breaks it first and get that positive value. Now, once again, I won't push you as far as repeated games. I'm just trying to give you a little bit more of like insight of what happens in the real world, and how if you continue to take like econ courses, or honestly even some of your like finance courses and stuff, you'll probably start to talk about game theory. You would kind of start to look at these repeated models. Okay. So it's not always just like a one-time period thing. You could kind of model multiple time periods, and there your payoffs just get higher. If we always agree that if you hold true to the agreement, I'm going to keep on holding true to it. But as soon as you burn me once, I'm not working with you ever again, right? That's kind of what this would depict. Right? So in practice, we see firms adopt this kind of tit for tat strategy. So I'm going to mimic whatever you do. So if you keep on selling at this higher price, hold true to this cartel agreement, I will continue to work with you. But as soon as you deviate from that one time, as soon as you break that agreement once, I'm never going to kind of hold that agreement with you ever again. Right? So it's kind of good news for us, because if they break the agreement, we get back down to perfectly competitive prices. Okay? So that was kind of that duopoly kind of thing about two firms, why they might cooperate. Okay? So I'll give you a slightly different example where we're not thinking as much about markets, and this will kind of I'll connect this with what we'll talk about later today, which is not just these games where firms are making simultaneous decisions. We'll also talk about sequential models, right? So for now, we're still looking at firms or individuals making decisions at the same time. So let's say I've got a research and development example where if I put money into research and development, I spend $9 million. The additional money I can make is $10 million. Right? So what would be like the gain, or what would be the profits there? 1 million. I gained 10. I spent 9. 1. Right? Now, if we don't have any patents, right, and we can steal or we can mimic what other people are doing, if I don't put money into research and development, but the other firm did, what are my profits going to go up by? Well, if I can steal their technology, how much are my revenues going to go up by? 10 million. What did I have to spend? 0, right? So if the other firm invests in the research and development and I don't, as long as there's no patent law, I'm going to gain a lot more. If we both invest, maybe there's like, I come up with a slightly different technology or cost-cutting technique than you did. There's kind of synergies of our research and development. So maybe we don't just see an additional 10 million, we see an additional 15 each. However, each of us had to spend 9, so each firm's profits there would go up by 6 million. So we've got 2 decisions: invest, not invest. We have all the payoffs. I could put this into a normal form game. Now, I said this is an example of what we call in game theory a chicken game. It's the same idea as if we're running at each other. So the game of chicken on the playground where we're running at each other and we either go left or right. Well, the only 2 equilibrium in that game is if we choose opposite directions. But there are 2 equilibrium. I could go right and you go left, or I could go left and you go right. So kind of foreshadowing what's probably going to exist if this is a chicken game: multiple equilibrium, right? So we'll kind of think through how we would identify these equilibrium. So once again, I think maybe it helps for me to write these out as opposed to just doing it all up on the screen here. So firm 1 can put money into research and development or not, right? So we had 6, 6, 0, 0, 1, 10, 1, 10. Okay. So these I'm just writing out, and I think that's millions. I left off the M's here for the sake of just, it's not going to change anything when we actually compare less than or greater than. So here's firm 2, here's firm 1. If I'm firm 2 and firm 1 puts money into research and development, well, if I can just steal their technology before we even look at the payoffs, what do you think it's probably best for me to do? Just steal it and not put money in myself, right? So sure enough, 10 is greater than 6. What if they don't put money in? Well, if I don't invest either, I don't get anything. Well, 1 million is better than 0. I would actually invest. And then what about firm 1? If firm 2 chooses to invest, I'm just going to steal their technology, not spend any money. But if they don't invest, well, if I don't invest either, nothing changes. Okay, 1 million is better than 0. All right. So here I've got an example where I've got 2 equilibrium. Now, what do these 2 equilibrium represent? Both of them are where one firm is investing and the other isn't. So we don't know which firm is going to invest, right? We don't know which one of these equilibrium we're going to end up in. But once we end up in them, there's no incentive that pulls the firms away from those points. So we know that one of these equilibrium will exist. One firm will be investing, one firm won't. We just know which firm that's going to be. Okay? So once again, this is an example where in these games, you can have multiple equilibrium. Okay? Any questions? I know I'm going through a little bit quick, but hopefully these are getting kind of easy to kind of see. We're solving them all the same way. Okay. Any questions here before I keep moving? So this would not be in the slides, but it looks a lot more like the real world. So I set this up, simultaneous decisions. That's actually pretty, a lot, most firms make research and development decisions at the same time. So let's say here, we have the same payoffs if we both, well, I could even do it this way. Let's say we can't use each other's technologies. So if I put money into research and development, I had to spend 9 million, I only got an additional 10. So we're kind of doing it worst case scenario. If I can't use the other firms, whatever they came up with, there's like a patent on it. There's no like synergies, right? And so instead of going up to 15 million, we're only going to be able to still just earn an additional 10. But we had to spend 9 million to do that. Now, instead of the scenario where I can just steal their technology or whatever they came up with, let's assume that when firm 1 invests in research and development, they get the additional 10 million, they spent 9, so they're still going to get kind of 1 million here. Okay? if I put a penalty on the other firm and say, look, if you don't invest and you steal their technology, you're going to get not 10 million. I'm going to actually impose a huge cost or legal like consequence on you, right? So if I impose like a legal cost to them, if they steal another firm's technology, what have I done here? You know, I'm just choosing some negative value, right? Some huge cost where it's like, look, if you steal their technology, even if you make some money, you're going to have to pay a large fine to the government. Right? So I've imposed an additional cost through the use of like patent law. Well, what about here? Well, there, if I'm investing, I get $1 million. If they steal my technology, I would be imposing like this huge cost. So here, what would my kind of equilibrium be? So what should firm one do? Well, actually here, this is an example. If you had the same value, you would actually circle both. We would say the firm is indifferent. Okay. What about here? Well, 0 is better than -10. Right? And then what about here? 0 is better than -10. Kind of 1 here. So once again, we end up with multiple equilibrium here. But in some sense, this is better. We're either going to see both firms investing in research and development, or we're going to see both firms not. So just imposing different costs, we've completely switched the equilibrium. Right? And that's because the equilibrium are all dictated by the incentives that exist. If we're just worried about profits, if you kind of change the costs or change the revenues that these firms can generate, changing their profit levels, we can change the equilibrium of the game. So that's why we see the government use things like patent law. So we're trying to switch the equilibrium to be from where only one firm is investing to both firms are investing. Right? And you know, if we want to ensure we don't end up here, what could the government maybe give? Subsidies so that if I don't invest, I'm actually like, you know, I'm, oh wait, what did I do? I could say like, let's say if I'm not investing here, how could I incentivize, what do I want? I want firm one, right? So if I'm not investing for firm one, I could say, oh, we'll give you like some money if you invest here or something like that. Adding in revenues, switching kind of the value so that I end up pushing there to only be one equilibrium, right? I won't like do something like this where I give you an additional cost. I'll give you like whatever the payoffs are. But I just wanted to kind of show you like by imposing additional costs, we can actually switch where those equilibrium are, okay? So what do I want to say here? So this would kind of be like a relevant example with like patent law where you just have to pay like legal restrictions. If any of you are interested in, this is somewhat related. I mean, it's related to what we're talking about in economics. If you have a business degree, if any of you are ever interested in like pursuing law, I'm going off on a bit of a tangent here, but I did it for the first class and I think it's worthwhile. If you're interested in law, like patent law and stuff like that, there's not a lot of people who have a law degree and can be good at the way that lawyers think, but also have a really good understanding or have like a good business background. So what do you think is true about the supply of people who have both those skills? It's going to be pretty low. If supply is low for a product, what would that do to its price? Increase it. What is the price that you would be asking for if you had that skill set? You're the product. Your price is your salary, right? So if you have any interest in going into law with a business background, like things like patent law, you can make a lot of money, right? Because you're a very low supply worker, right? There aren't a lot of people that would have both of those skill sets, right? Anyways, I digress, but this is a related patent. Also, start to think about things like what we're talking about with markets. Like that applies to like the price of goods is essentially, you could think of you're the good, that would be your wage. How can you ensure your wage is high? Put yourself in a group where there's a low supply of you, right? Or in a group where there's really high demand, right? Anyways, I digress a little bit, right? So we've got kind of this game. We already looked through this. We built this out. So I don't think I went through an example yet where we had this be possible, but I wanted to at least make you aware that it can be, and maybe on a quiz or an exam question, this could be a possible answer. So if I'm playing rock, paper, scissors, how many of us have win. Ultimately, you kind of already inherently know this. The game of rock, paper, scissors is what? You're trying to win. It's kind of a crapshoot, right? You're just guessing what the other person is going to do, right? In fact, you could build this out. We don't always have to have just 2 decisions. You could build this out to be like 3, 4, 5, 50 decision matrices. It becomes, you have a lot more work to do, but you can still solve Nash equilibrium for these games. So, for example, if that second person throws rock, inherently you know, what should the first person do? Well, what beats rock? Paper. So the ones represent I'm winning. So if I throw paper and they throw rock, person 1 wins. If I throw scissors, they beat me. -1 is I lose. If we both throw the same thing, nobody wins, nobody loses. The payoffs are 0. So you could go through, if person 2 throws rock, person 1 should throw paper. Person 2 throws paper, person 1 should throw scissors. Person 2 throws scissors, person 1 should choose rock. Identify those best responses. You then go through and do it for the other person. Person 1 throws rock, person 2 should throw paper. Person 1 throws paper, person 2 should throw scissors, etc. Well, notice here, once again, non-technical way of identifying a Nash equilibrium. But do I have a box that has 2 circles in it here? No. So you can end up, if you don't have any possibility that we're both best responding to each other's best response, in the game of rock, paper, scissors, if we both threw, you throw rock, I throw scissors. If you then give me the choice to change my decision, am I going to keep throwing scissors? I mean, if I do, I lose. I guess if I want to lose, but if I want to win, I'm going to change my decision, right? So there's no point where we would be in an equilibrium. There doesn't always have to be a Nash equilibrium. It can be the case, and we call these usually like zero-sum games. Someone wins or loses, or I guess we have a draw, but no one's going to win, no one's going to lose there. You can end up with 0 Nash equilibrium. Now, that is a possibility. So if you're looking at a question, multiple choice, and you see one of the options is there's no Nash equilibrium, don't just automatically rule that out. It is possible depending on what the payoffs are. Okay. Is that, I know I went through that kind of quick. Are there any questions on that idea? Okay. All right. So we're now going to transition to thinking about what we call extensive form games. Okay. So extensive form games, one of the things I said at the beginning of last class, and then I kind of don't focus on it, is the decision, the timing of the decision matters. So all of these normal form game matrices, we're always assuming decisions are made at the same time or simultaneously. With extensive form games, we're assuming that people make decisions sequentially. So person 1 makes their decision and then person 2 responds, right? So the way we're going to solve these is called backward induction. We're going to use decision trees to kind of depict these, or through some examples, and I think this idea of like what backward induction is will make a little more sense. So we'll start out with a really dumb, easy example first, where we have what, Charlie Brown, right, and Lucy. So you've never seen or read the comic book. It's like very old. I don't even know, 50s or 60s. I don't know how old it is, right? But the running joke, and then it was made into a cartoon, is that Charlie Brown always goes and tries to kick the football, and then Lucy, who's holding it, either pulls it away or lets him kick it. Well, in the cartoon, she always pulls it away. Ha ha ha, very funny, right? But you can think through, what should Charlie Brown be doing in this game, right? He's making the decision first. He's running towards the football. He's going to kick it, or he could just like not run towards the kick, right? He can either accept or like reject this offer, like to run and kick the football. So that's person 1 you start out with on the top. They're making the decision first. Once he makes his decision, Lucy then has a decision to make second. I can either let him kick the ball, or I can pull it away at the last second. We're then going to have corresponding payoffs, right? So if he just rejects the offer, nothing happens, right? You got to think about the utility of both individuals is just 0. There was nothing good happen, nothing bad happen. If he accepts the offer and Lucy lets him kick the ball, he gets some level of enjoyment by kicking this football and looking like a football star, right? She is not amused. Right? Okay, kick it. It doesn't really give me any additional happiness. However, if she decides second to pull the football away at the last second, he falls down, negative utility to him, but she's amused, positive utility to her. So the way that we'll do this is think about for each possible choice here. Now, I made this one easier. We really only have one part of the decision tree. I'll go through an example in a second where we have multiple. But we're always going to start out with the person making the decision second. So that's Lucy. Is she going to let him kick the ball or not? Well, if she lets him kick the ball, she's not amused. If she pulls it away, she is amused. So what's better for her? To be amused, positive utility. We know she's going to pull that football away. Okay. Now, what we'll then do is say, knowing that second person's optimal decision, best response, if Charlie rejects this offer, nothing happens, his utility is 0. If he accepts the offer, if he knows Lucy well enough, he knows that she's always going to choose to do what? Pull that football away. So he knows that this isn't even a possibility. Like, this is never going to happen. So I'll work through some examples of what I would usually do here, is I would just cross this out. I know this won't be an outcome. So he's basically choosing to reject the offer, have utility of 0, or accept the offer, in which case he knows she'll pull it away, he'll fall down, he has negative utility. So what should he choose to do? Reject the offer. That's why the running joke of the cartoon is like, he's an idiot. He keeps accepting the offer. He's actually putting himself in a scenario where he's not better off. Okay. So this is just a very easy, kind of dumb example. Let's kind of make it a little bit more complicated, right? So I've got this one in the slides, but we'll kind of talk through it here. I think I can give you a slightly better way of looking at this. So let's think about this as the existing firm, firm 1. They can choose to either set a monopoly price or a lower perfectly competitive. It doesn't have to be perfectly competitive. I think I'm going to use the extreme here just to make it a little bit easier, but basically a high or a low price, right? Firm 2, who's thinking about either entering or exiting this market, will then make a decision based off of, I say entering or exiting, sorry, entering or staying out of this market. They're not in it yet. Whatever price that existing firm sets, they'll either choose to enter the market after they see it or stay out, right? I mean, firms do this in practice. Like if I see, that, I don't know, all the, let's say, I just keep seeing a lot of this stuff. Let's say like I see the prices that these power wash, like you see like ads for people that will power wash your house, like on electric poles all the time. If people are charging really high prices, I might decide, am I going to enter that market or not based off the current price that they're charging? So firm 1 is the existing firm. They make their decision first about what the price is. Then other firms who are thinking about getting involved in that market make their decision second. So person making the decision first is on top. Person making the decision second is on bottom. If they set a high price and this other firm enters, the profits of firm 1 and the profits of firm 2 are going to be what we are interested in here. So I'm just going to write these out and we'll kind of think through why they would be what they would be. Oh, sorry, I don't want to do equals here. Well, I do here, so we'll hold off. So if they set a high price, another firm enters and undercuts their price, that firm that enters is maybe going to get all the demand, right? Positive profits. Where the existing firm, where they already set their price high, nobody wants to buy from them. Okay. Now, if the other firm stays out, they're setting the monopoly price, their profits are going to be positive. The firm stayed out, so their profits are 0. Right? If the existing firm sets a low price, perfectly competitive price, and this other firm kind of enters, well, now we're setting a low price and there's 2 of us, right? We actually are going to both end up with negative profits. Okay? And then if they set the competitive price and I stay out, well, if I'm setting the perfectly competitive price, what are profits? Perfectly competitive profits are 0. The firm stayed out, so their profits are 0. So if this is our kind of payoff structure, how are we going to solve for what the Nash equilibrium of this game would be? Or technically, I think if you look in the reading, we call this a sub-game perfect Nash equilibrium. But we'll solve this for the first, we'll solve this from the bottom and work our way up to the top. So the person making the decision second we'll figure out what they're going to do first. So let's assume that the existing firm sets a competitive price. What should firm 2 do? Well, what's better, negative profits or zero profits? Zero. Or should I just throw this away? I know it doesn't work. So they're going to stay out, right? I'll pick it up later. Don't worry. So I'm going to stay out in that scenario. If the existing firm sets a high price, what should firm 2 do? Well, what's better, zero profits or positive? Positive. So they're going to enter the market. So I've determined what the optimal decision would be for that second firm, the person making the decision second. Knowing this, so one thing we assume in all these games is everybody knows like what everyone else's payoffs would be. So firm 1 can kind of anticipate based off of their data what firm 1's payoffs would be if these were the scenarios. So firm 1 says, well, look, I know if I set a high price, firm 2 is not going to stay out of this market. So this is never going to be a possible outcome. I also know that if I set a perfectly competitive price, this firm will not enter, like they're going to stay out. So I know that this isn't even a possible outcome. So the decision that firm 1 is really trying to make is if I set a high price, I know firm 2 will enter and I know my profits will be negative. I know that if I set a perfectly competitive or a lower price, that firm will stay out and my profits will be zero. So what am I going to choose to do? Profits of zero are better than negative. So here we end up with our sub-game perfect Nash equilibrium. We're not going to really use that terminology for us. Just our Nash equilibrium is going to be that firm 1 chooses to set a lower perfectly competitive price. Firm 2 stays out of the market. Now, what is this a good or a bad thing for the firm? Well, profits are zero. That's not great. Who is this a good thing for? Consumers. Even the threat of other firms entering this market have caused us to go from outcomes where we could have seen, higher prices to where we know profits are going to be equal to zero for the firm, and that's going to be at a perfectly competitive price. That's going to be better for consumers. So just the threat of another firm entering could incentivize the existing firms to set lower prices to try to keep them out of the market. Okay. Now, will they truly set a perfectly competitive price? They're probably still going to earn some level of positive profits, but at least they're going to be choosing a price that's closer to that perfectly competitive price. When we look at the actual values of like firms in the industry, these probably won't be zero. These will be like just a much smaller number, a smaller positive value. And so we won't get quite to that perfectly competitive point, but we're going to be getting closer to it, right? Prices will be lower, which would benefit consumers. Okay. Any questions about how I kind of solved this one, kind of working backwards here? Do we think this is easier or harder than the normal form ones? About the same? About the same? Okay. Let me think. So we've got this. We've identified our equilibrium. What else do I have here? Yeah. So this one, before I show this to you, this is kind of a dumb example, but I'm just going to show you that you can work through it and you figure out what that intuition tells you. We're playing that rock, paper, scissors game, and I have to go first, and then you get to go second. Who's always going to win? Person going second, right? So you can actually build out a game of rock, paper, scissors with the payoffs of 1, I win, -1 if I lose, 0 if we throw the same thing. And what you can see is, all right, if person 1 throws scissors, what should person 2 do? Play rock. Person 1 plays paper, person 2 should play scissors. Person 1 plays rock, person 2 should throw paper. So you can solve this sequential game. Intuitively, we kind of know we're going to end up in equilibrium where person 2 always wins. But here is an interesting one where, well, person 1 basically would cross out all these other possibilities. They say, look, if I play rock, I lose. If I play paper, I'm going to lose. If I throw scissors, the other person gets to go second, right? We're not making the decision simultaneously. I'm going to lose. So what am I going to throw? Who the hell cares? I'm indifferent. I'm going to lose no matter what. So here we would have multiple equilibrium, but we don't know which one we're going to end up in, right? We just know that whatever the first person throws, the second person can always beat it. Okay? Now, I don't know, there's not a lot of examples that would like look exactly like this in the real world in terms of like vertical we're making. But if we do have, I'm sure there's like some context of like workers that make decisions, where you could end up with multiple equilibrium where the the person going first always loses. We would call this like a first mover disadvantage, right? Or a second mover advantage, right? Whoever gets to make the decision second is always going to be a little better off. Any questions on this idea? Shouldn't be too bad. So I've got one more example, and then we'll kind of look at the quiz. So let's say I had this thing set up where I give you, oops, let's say I choose two of you. I say, I'm going to give you $100. You can offer the person next to you increments of one. Right? So you can offer them $1, $2, $3, $4, $5. If they accept the offer, you both get to keep whatever amount of money. You know, if you offer them 3, you keep 97, they get 3. If you offer them 50, you get 50, they get 50. If they reject your offer, neither of you get anything. Okay. So let's think about kind of what our equilibrium would look like in this sequential game. The first person gets to make the decision of how much to offer. The second person gets to either accept or reject that offer. Okay? Now, just for the sake of making this a little bit, I think, easier for you guys, we'll assume that you can't offer them nothing. Right? You have to offer them the lowest amount you can offer them is $1. So here I've got person 1. They can offer the second person $1, $2, $3, etc. I'm just going to do these 3. You could kind of continue to go, 4, 5, 6, all the way up to I could offer them 100, right? But we'll see that even just using these 3, we can kind of figure out where that equilibrium of the game is going to be. Okay? So person 2 makes the decision second. So once offered this amount of money, they can either accept or reject the offer. Okay. Everybody with me so far? Okay. If they accept, so let's say I offer them 1. Actually, if they reject, what are the payoffs always going to be? Nobody gets anything, right? If they accept the offer, they get to keep $1. The first person, they had 100, they offered them 1, they get to keep 99. What about here? Well, they keep 98. They offer them 2. The second person gets to keep 2. 97, 3. You kind of continue to go on down the line. Okay. So if I look at this, what is person 2's best response? If the person 1 offers me $3, if I reject it, I get nothing. If I only care about money, what am I going to do here as person 2? 3 is better than 0, so I'm going to accept. If I only care about money here, what is person 2 going to do? 2 is better than 0, I'll accept. Here, 1 is better than 0, I'll accept. Okay. So basically, if all they care about is money, person 1 knows that no matter how much I offer them, person 2 is always going to accept. So what am I going to offer them? The lowest possible amount. Now I can prove this to myself because I know they're never going to reject. I know these are never going to be possible outcomes. So we figured out the second person's best responses. We're now going to figure out the first person's best response to those best responses. It's kind of weird to say, but if I offer them $1, I'm going to get 99. If I offer them $2, I get 98. 3, 97. What's going to be better off for person 1? To offer them that lowest possible amount. Okay. Everybody with me so far on this? Okay. So that's how we would solve a game like this. Our Nash equilibrium is person 1 offers $1, person 2 accepts. Now let's say that the person 2 doesn't just care about money. In practice, if I set this up and the person next to you offered you $1 and you know they could have offered you like even an even split of 50-50, what might you do? reject it out of pure spite. I don't care that I'm getting to keep $1 here. If I reject the offer, I don't get nothing. Person two, I get a huge value of like screwing you over, right? Because you offered me such a low amount that the utility I gained from rejecting your offer is way more than the amount you offered me, right? So now what would their optimal decision be? Not to accept the offer, but to reject it. So you can see when people don't just care about money, you would actually possibly change the equilibrium of these games because you're changing the player's best responses. In fact, if you wanted to go through and like just put a value to it, like this person I said valued spite at $10, what would have to be the amount I offer them in order for them to accept? 10, they'd be indifferent. So I might offer them, just to make sure, $11, right? In which case, okay, I valued my spite at $10, but I was being offered 11, I'm better off, right? So they actually run experiments like this in the lab. So I gave you guys the QR code one class about doing the economic experiments. They do kind of games like this. Like they do a lot of game theory stuff. And what they found is in a game similar to this, now they don't give you $100. I think it's like, they do smaller increments. But basically it's like, if people are offered anything below a third, a lot of people start rejecting, right? They value spite quite a bit, right? So like if you start to offer someone like $10, $15 in the examples, like out of 100, you would actually end up seeing the equilibrium is that you actually need to offer them closer to like 30, right? Otherwise they'll reject at any value. Now every individual is a little bit different. I'm kind of talking about averages, right? Here, if we just care about money, the equilibrium of this game is I'm just going to offer you the lowest possible increment. If people care about things more than just money, well, that's going to change the payoffs. It could change where my equilibrium is. Okay. Any questions on this idea before we keep moving here? Yeah.
What would the market for the biggest concept of this one? Regardless of price, every firm has a demand and is making profit. Like there's a firm which charges higher price and is still making profit, and there's a firm which charges lower price and they are also still making profit. How would the market play out in that?
I mean, it would all depend on what the actual demand and what your payoffs are, right? So if the firm's profits are lower, so if the existing firm's profits are going to be lower by that other firm joining, then they're going to make a decision that's going to increase their own profits. That might keep that firm. So it doesn't matter if they're zero or they're just a smaller positive amount. It just matters whether or not the profits are smaller than they were before, or if they're larger than they were before, that firm thinking about entering. So I can't give you like an exact answer without like, you would actually have to know what the demand curve looks like and what the actual profit levels are. Which is why I'm using this kind of two extreme markets we talked about, monopolies versus competitive, because that intuition would still apply to all the things in between. It's just directional changes. We just know our profit's going to be lower or our profit's going to be higher, right? And then we can identify what the best response is based off of that. So curious, talking about the class, I can kind of try to work out a little bit more. I just want to make sure we have a little bit of time to kind of go through. Okay. All right. Any other questions before we keep moving here? All right. So got one more thing that I want to do. We'll do it relatively quick. We'll publish this quiz. Should be on the main Canvas page. I'll kind of walk through one with you, and then I've got what I think is kind of another fun example with game theory. We can start to think about things here. And actually, well, I think we'll have enough time. All right. So to make sure we all get this in on time, so I think I have it set to be 10:40. Before I talk through this, we'll work through this example, and then I'm going to have you kind of do the second one. So I'm going to tell you the answer right now is that neither firm invests. So we'll talk through why that's the answer, but I'm giving it to you now so you can get it submitted on time, because I'm a little bit more focused on the second part to make sure you can think a little bit about it, and we'll have enough time to kind of review it. So we'll review this problem in just a second, but I'm letting you know the answer is that neither firm invests here. Okay? Is everybody with me? So the one that I want you to give a little bit of time to thinking about next couple minutes is, let's think about if you are all going to guess a number anywhere between 0 and 100. If you're wanting to win the game, the way you win the game is if you guess half of the class average. So if I were to like, whoever wins this game, I'm going to give you 10 extra credit points. I'm not doing that. But I'm saying if there was an incentive, right? That's your goal, is to try to win this game. You want to guess half of the class. So the class average number guessed was 70. The winning value would be, if you guessed, 35. So try to guess a number that is going to be half of the average number that everybody else in the class would guess. If you can guess that number correctly, you would win this game, essentially. You want to guess half of what the class average number guessed is going to be. So think about that for a minute or two. Kind of make sure you're getting that first question in as both not investing. And then we'll talk through the kind of game theory that would be involved in this question. And we'll also kind of work through this additional extensive form game that we have up here. Okay. So you're trying to guess the number that would be half of the average number guessed by everyone else in the classroom. Okay. And it has to be between 0 and 100. Okay. All right. Okay. So I have it set to be due at 10:40. So everyone got that submitted. Okay. If you want to think about it for the next couple, just make sure you're getting it submitted before 10:40, that second question. I'll start working through this first one, and then we'll come back to one that I think might have piqued more of your interest, right? So let's say I have this extensive form game where I now have research and development decisions, but it's sequential. So firm one makes their decision first, and then we're assuming, once again, no patent law. So then as a response, firm two is going to make their decision. If firm one invests, what should firm two do here, right? We're going to solve this using backward induction. Solve it for whoever's making the decision second, which is firm two, whoever's lower on that decision tree. So if firm one invests, what should firm two do here? Quicker you answer, we'll probably also get out of the way, right? If they invest, they get 50 million. If they don't invest, they get 60. So they would not invest. So if I have this written out, once I've identified person two's best response, I know this is never going to be a possible outcome. What would I do? Scribble this out, right? On the other side, what if firm one doesn't invest? What should firm two do? If they invest, they get -20. If they don't, they get 10. They should not invest. Scribble this out, right? I think the way I had this set up was like different costs to investment of these two firms that could result in these payouts. So now I say, okay, I've made firm two's decision. What will firm one do in response to that? Well, if firm one invests, they know that firm two is always going to do not invest. So I know my payoff would be -200. I also know that if I choose not to invest, firm two is always going to choose also not to invest, in which case my payoffs would be 10 million. So which one's better, 10 or losing 20? 10. So our Nash equilibrium would be that firm one and firm two don't invest. Once again, person one's payoffs are always on the left. Person two's payoffs we're always going to write in the right here. Okay. So that's why that Nash equilibrium was both firms choose not to invest. Okay. Any questions on that one before we keep moving here? So as long as you get a response in, you'll get the full points for it. Yeah. So that's why I was saying, sorry, I thought it wasn't clear. Get it submitted here before 10:40. I'm going to talk about it now. I just wanted to make sure we're getting a number in. There's no right or wrong answer to that second question. Okay. Has everybody got a response in here? All right. Before we get too antsy, I'm going to get you out of here a little bit early still. Just want to kind of talk through this. I think it's somewhat interesting, especially like if you want to do like finance majors, you would start to think about this. It's actually really matters. So if everybody in this room guessed a random number between 0 and 100, what would the average of the class be? 50. So what number should you have guessed to win? Half that or 25? But if everybody knows that, what's the new average going to be? If everybody guesses 25, the new average is 25. So what number should you have guessed to win? 12 and a half. But if everybody knows that, what's the new average going to be? 12 and a half. What number should you have guessed? 6.2. You kind of can continue that all the way down, that if we all knew that this was how the game is played, what should all of us guess? Essentially, 0. Right? Now, this is, you can prove mathematically what you should be guessing if everybody is thinking about this correctly. What we see in practice, so they've run these experiments, and this kind of sounds like negative, but they call them level K thinkers. So a level 1, not to say if you did this, that this makes you less than. If you're a level 1 thinker, you would have guessed the number of 25. You would have said random numbers, everyone, the average is 50, I'll guess 25. You're a level 2 type thinker. If you said, well, everyone knows that, everyone's going to guess 25, so I'm going to guess 12.5. You're a level 3 thinker. If you said everyone's going to know that, I'm going to guess, and then I kind of continue down to it. If you're a level infinite thinker, you would have guessed 0. Right? So you can actually, I forget the breakdown, but they've run these experiments and they've actually looked at like the general population and seen how many level 1, 2, 3, 4 type thinkers there are, like what that distribution looks like in the population. Now, they've also done this with college students, like that's because you're easy to recruit because you don't have a lot of money. So what do you actually think is probably true about your average level K type thinking relative to the population? You're slightly higher, right? You're like level 3, level 4 type thinkers, where a lot more of the majority of the population is level 1, level 2. But this intuition that you're using, right? You probably don't even realize you're doing it. You're really doing a decision tree, right? And it's pushing you down to that point where if everybody else is going to guess half the average, I need to make sure I guess the next lower value. So as long as you got something submitted there, I gave the answer to question 1. Any response for that second question will be counted as correct. Hackback number 4, module 13 reading, module 12 quiz, due at the end of the day, Monday. A great Easter weekend, and I will see you guys on Tuesday.